Our final student speaker of the day, no pressure, is Dawson Wright from Texas Tech University, who is studying electrical engineering, and he's an LRGF fellow who is doing a residency at the Nevada National Security Sites.
Thank you for that introduction. So, hello everyone. Today I'm going to be presenting on a small part of my PhD work, impact of magnetic cores, impedance variations, reset techniques on linear transformer drivers. And right at the top, I'd like to thank the NNSS, the LRGF, for allowing me the opportunity to do my PhD and supporting me through this process. As well as I'd like to thank Zach Shaw. He's my mentor at the National Security Site, and he actually helped come up with some of the ideas that I'll be presenting on today. So the motivation was we wanted to design a fast rise semi-high voltage system that we could test for various number of things, insulation breakdown, gas breakdown, any other kind of physical phenomenon testing. As well, we had some specific parameters that we wanted to achieve, so 50 to 500 nanosecond variable pulse widths, a rep rate of single to tens of kilohertz, and minimum of 20 kV output, as well as trying to understand some of the magnetic behaviors that happen in these LTDs, and I'll go over kind of how these LTDs work, and some of the effects of the transmission line impedances on the voltage transfer and efficiency, as well as the rise times. So a little bit, for those who don't know what a linear transformer driver is, it's a bunch of MOSFETs, in this case, and capacitors. And they're all in parallel, symmetrically around the magnetic core here. And you actually have two different individual current paths. So you have the inner current path and the outer current path. And in this case, the magnetizing current, which is on the inside, and then you have like the load current on the outside. And so what happens when you switch these on is you get a small current flow on the inside, but what the magnetic core does is it acts as a magnetic choke. It leaves, or it allows the high impedance path here to actually push the main current path to the other side of the conductor. And what that does is it allows the current density to go along the inner conductor here, which will then couple voltage onto the transmission line of the stock. So we did some single-stage, multi-stage testing and using just a simple trigger to trigger all 10 stages. So the LTD acts a lot like the marks in the sense that you charge up in parallel and then discharge in series. And so this is just the trigger board that was made to trigger all 10 at the same time. We actually had to make a custom voltage probe because the voltage probes we were using weren't fast enough. And so we were getting a lot of inductive spiking in our measurements. And for the current probing, we use the CVR. So this is the, that's not right, but okay. This is just kind of the layout. So there's 10 bricks here, each with a MOSFET capacitor, and they all flow underneath the magnetic core. So for a single stage, we got 2.4 kV max, 1 kiloamp max, and then a 50 to 100 nanosecond pulse width. It was supposed to be 3 kV originally, but I kept breaking the capacitors. So these little ceramic capacitors actually cannot take the DVDT, and so they would actually physically explode when we were firing them. So we had to go find a different capacitor at a slightly higher voltage that could handle the actual stress that it was being put under. So the brick design, MOSFET, capacitor bank, freewheeling diodes. This freewheeling diode found out that very important, if you don't have this, the DIDT when your MOSFET switches off will also blow up your MOSFET. And so this loop here is very important. So when you switch it on, your MOSFET closes and you get a high voltage path here. And then when you switch it off, you have to let that magnetic energy that gets stored up in the core discharge somewhere, and it discharges through that freewheeling diode. So these are some of the results from a single stage. So we have different voltages, all very flat top, you can see. And then over here we have different pulse widths. And then we go into saturation on the magnetic core. This is just some statistics showing that as you increase voltage, you actually get slightly higher rise times. This is mostly due to the MOSFET struggling to turn on fully at the higher voltages. You can see that even at the higher voltages, though, we're sitting around 8 nanosecond rise time for the system as a single stage. It actually doesn't get much higher than that as you increase in stages, which was something I wasn't expecting. I was expecting there to be a little bit more delay or a little bit higher rise times as you increased the number of stages. So this slide, I know there's a lot of information on this slide. I'm going to start over here in this corner. So this was the initial set for a single stage. It is a 2-inch height, 51 millimeters, a transmission line. That inner stock impedance was 75 ohms, and we had a gate voltage of 20 volts. And then each of these represents a different type of magnetic material. I'll talk about that on the next slide, but for now, we'll just talk about the parameter sweep we looked at to optimize the LTD. So going from a 2-inch board height, so that's stage-to-stage height, to and a 75 transmission line, ohm transmission line, we lowered the transmission line impedance to actually match the load impedance here. And what that did, we didn't get any faster rise time, but we did get a slightly higher voltage transfer out. So again, we're optimizing. So at baseline, it was 96% energy efficient. Just by changing the transmission line impedance, we actually bumped up to around 75.5. So it doesn't sound like a lot, but we're optimizing. So the next step was, well, what if we shorten it? So we lower the inductance, we lower the actual physical distance the transmission line has to transfer the energy, and we get slightly faster rise time. So we went from around 9.5, 10 to around 8.5, 9. And then another knob that we have is the actual gate voltage. So the voltage that goes to turn on the MOSFET. I upped that to 5 volts above the maximum rating for that MOSFET. So does that derate the MOSFET a little bit? Yes. These are very short pulses. 50 to 500 nanoseconds is not that big of a deal. So going to 25 volts didn't have any lifetime effects that we noticed, at least. But what that did is it centered our voltage efficiency a little bit higher, as well as we gained another nanosecond of rise time. So now we're under 8 nanoseconds across the board for each of the magnetic materials. So briefly, this is what the waveforms look like at 550 nanosecond pulse. This is to show the 3 different materials. I'll talk about it in just a second. There's no real difference in rise time, and that's shown here, or flat top. The only difference is that the 3WL, which is a lower flux availability core, saturates earlier. So these are the 3 cores we looked at: 3WL, 3WH, 3WM. These are the same material baseline, so it's nanocrystalline, fine met Hitachi brand. The only difference is they're annealed. So there's a no field annealed, a transverse annealed, and a longitudinal field annealed. And all that really does is change the permeability of the material. And so going through these, the 3WH actually had the highest available flux. And that matters because we don't want the LTD to saturate. We don't want the core to saturate while we're pulsing it. Otherwise, we lose all of our voltage on the load. So most of the 10-stage material is that 3WH core. The other thing that we looked at is pulse versus continuous reset. And I'm going to skip the slide and I'll explain it here. So the continuous reset is basically you have a wire around your core and you're putting a constant 4 amps across it. And what that does is it allows you to, in between every pulse, you get to reset the flux availability in that core. And so at continuous reset, it took us about 200 microseconds to fully reset the core. And the pulsed reset, so this is a reset, there's some delay, we pulse it with high voltage, then we reset it again and do it again. And we compare the flux before the reset and then after the reset. And so overall, the biggest difference is it took twice as long to reset that core. And why that's important is there is some activity in the field saying, well, if we could take out that continuous reset capability and make it a pulse reset, we should be able to basically put everything as a single unit. So right now how continuous resets work is you have basically a giant wire around every single one of your cores. And it has to be external to the system. And so in order to get rid of that externality, we can put these pulsed or active resets onto the board, which is this right here. So that's really the only advantage, it seems. It seems like continuous reset performs better overall. So that's, we reported on that in one of the papers because there was some arguing amongst the scientists, let's say. So this is just an example of, so this is a 5 megahertz burst. So every 200 nanoseconds, I pulsed a 30 nanosecond. This is 3 kV, so 3 stages charged to 1 kV. And then this is showing that we have individual board control of the LTD. And so this is extremely important because the LTD is a very generalized pulse power source. It can do very quick rise times, variable pulse widths, variable voltages. We also want to be able to pulse shape in whatever way we want. And so this is just proving out that if you have 10 stages, you can make quite a few different pulse shapes if you wanted to. So going into the 10-stage results, so we got out here, there's 3 different graphs here, each with a different load, but the stock impedance is 23 ohms. And what I wanted to show here is this is the transmission line effects part of the LTD. So the transmission line originally was not assumed to be part of the LTD. The transformer part of the LTD is actually a misnomer. It's not a transformer. And so it was thought of originally that, oh, well, the transmission line is not going to affect anything. It's just a transformer. Who cares? Well, this is proving that it does matter because at these very fast pulses, so 50 nanosecond pulses and quick rise times, when you're mismatched your load and your stock impedance, you get these reflections in your transmission line. And so when the mismatches get really bad, so this is 4 times the stock impedance over here, you get these spikes. So if you're rated for 24 kV, and you get a 26 kV inductive spike out on your load, you may damage whatever you're trying to test. Now, in some cases, you may be able to deal with that, and it's not that big of a deal. But if you're trying to do fine, precise science, you don't want this. You want something that looks like this, right? So matching your load impedance to the stock impedance is very important. This is just another comparative waveform of the different loads compared to the stock impedances. So flat top, less flat spikes. And then over here at a 51 ohm transmission line, you get, so when it's actually under matched, you get slower rise time and less flat, but on the other side, versus that reflection or the spike here. So with that, this is we looked at a wide parameter space, and we really were just trying to see what knobs can we turn on this general pulse power device to optimize it, and as well as provide this was actually delivered to Nevada National Security Site for them to test with, so that was pretty cool. And so the final system was 10 stages, 24 kV, a kiloamp, and all the rise times were about 10 nanoseconds. And with that, I'm done.